Good morning, good afternoon, ladies and gentlemen. Welcome back to Mr. Lee Physics class. Ladies and gentlemen, let's look at the slide. So what we will learn today is related to magnet. We will learn about the magnetic field today. Ladies and gentlemen, let's say we have a compass and a magnet. Normally, magnet with North Pole and South Pole. When I put a compass near to the magnet at the North Pole, we notice that the pointer points to certain direction. Now, I will move around the compass, move the compass around the magnet. You observe the direction of the pointer on the compass. Now, when I move, notice or not what happened? Okay, point to the South Pole. You see? So like they are point to the South Pole, and then this will point to, okay, opposite side up. So why this happened? This is because the pointer of the compass show the direction of the magnetic field. The magnetic field actually is at that. Now we look at here. Here is go to the left side. This will go to the left side as well. But over this side is point to the right side. The other also point to the right side. Inside the magnet, okay, nothing. They didn't show it, but outside. Why? Because the magnetic field form is like that. North Pole is up, point to the South Pole. So from here, South Pole is in. So that means that South Pole is in, North Pole is out. That means that it's always point to this direction, this direction. How about the direction at the north and south in between? If here it's point to the right side, right? Right side. So you notice or not, it's follow the direction of the magnetic field actually. Observe this region. When I put the compass here, so we notice that it's follow the pointer of the compass show the direction of the magnetic field. Now, we go to the next slide. The Earth. Our Earth actually considered is a big magnet with the North Pole and the South Pole. We have the North geographical pole. If North Pole actually consider the magnet actually is the south pole of magnet. So at the North Pole of the, okay, at the north, so this means that at the North Pole of the Earth actually like the South Pole of the magnet. For the South Pole of the Earth actually is the North Pole of the magnet. They are interval, the magnetic pole. Now, let's look at the phenomena. This phenomena show that the sky with various color. This phenomena we call that is Aurora. Aurora phenomena. Aurora phenomena just happen at the North Pole of the Earth. It's never happened in Malaysia. Never happened in equator. Just not in the South Pole only. Why this phenomena happen? This phenomena happen because of the magnetic field. North Pole on the Earth with the strong magnetic field. when, okay, when the space produce the magnetic field. The magnetic field actually is from the sun. Magnetic wave from the sun move through the space when the magnetic field from the sun pass through the earth. The interaction between the magnetic field of the earth and the magnetic field from the sun is produced the aurora. The magnetic field produced by the sun and transfer along the space to the earth, we call that is the space wind. The space wind when interact with magnetic field, so we notice that the sky with various color. It's very nice, right? So this just happened at the North Pole of the earth. Ladies and gentlemen, in today's lesson, you will learn the magnetic field. You will understand the concept of magnetic field. Second objective, you will learn the formula for the force on the charge moving in a magnetic field, where we use the F equal to Q V times B. Ladies and gentlemen, you notice or not, the F, the V, and the B with arrow on the symbol show that that is a vector. Meanwhile, F, V, and B show not only with magnitude, but also with the direction. So this means that we need to consider the direction of the force, direction of the speed or velocity, direction of the velocity, and the direction of the magnetic field. Objective number 3, use the equation F equal to QVB, sin delta to define the magnetic field strength B. Study the motion of the charged particle in a uniform magnetic field. Now, this slide shows that the direction of the magnetic field. BB is the magnetic field. That means that the arrow shows the direction. We use the arrow to show the direction. View, okay, back view, what we can see that will be same, it is a cross. Front view, we notice that it will be a dot. So this, we show that if there is a dot, that means that the magnetic field now is out of our screen. If show that is negative, means while the cross now is go into the screen. Ladies and gentlemen, magnetic field into the plane of the screen is represented by a cross, where the magnetic field out of the plane of the screen is represented by a dot. Next. Now the X show that is the magnetic field. Why? Because they tell us that it's B. B now is going in. Q now, okay, a uniform magnetic field into the plane of the screen go into, right? So what happened to a positive charge move through? We notice that the positive charge, okay, positive charge will move and deflected to upward. So what happened is we notice that the force is like that. Because it's moving with a F, okay? And then there will be a force, cause always go to this side and produce a resultant force that is the resultant direction. the force. Okay. So now, how about the direction? Show that a charge move with a speed where the magnetic field is going in. That means that this will be the F. Okay, and this we use the what we use. Okay, we can use the right hand grip rule. Right hand rule show that, ladies and gentlemen, the force, okay, represented by our thumbs. The direction of our finger is from V to B. Once our finger cross replay, so that means that show that initially point to the B and move. When we cross our finger, we cross our finger means that we are showing the finger direction is point to the B. Okay, actually this, okay, this also can be represented by left hand rule. Whose hand? Fleming's left hand rule. Okay, you point, you show the Fleming's left hand rule where times is F, B is the first finger, second finger, middle finger will be the velocity. Okay, velocity show that the direction of the current, because charge is moving, positive charge is moving in this direction. That means that the current show same direction with the positive charge. So velocity, the direction of the positive charge will be the direction of the current. Now we look at here, a magnetic field replay. What happened? Okay, now it's going downwards. Now the magnetic field is going up. Okay, magnetic field is going up. That means that if magnetic field is going up, that means that we found that by using the right hand rules. Okay, the direction our finger initially, you see, initially show the direction of the V. Show the direction of the V. Okay, and then the magnetic field now is out of the screen. Okay, magnetic field is out of the screen, so we turn our hand to out of the screen. We notice that it show that the times show the direction of the force at this point. Okay. Next, we look at here. If there is a positive charge in the magnetic field, which going into the magnetic field, the direction of the magnetic field is into the plane, into our screen. Then what happened? Positive charge follow the direction of current. Okay, so that means that positive charge will move in this direction. Negative charge will be in opposite direction. Okay, opposite charge will be in opposite direction. Just now the right hand rule just obeys the positive charge. If negative charge, remember negative charge always in opposite direction with the positive charge. Next. Next, we look at here. If the F, B, and the direction of the charge, all of them are perpendicular to each other. All of them are 90 degrees to each other. So if all of them are perpendicular to each other, that means that the magnitude of the force is equal to QVB. B. Q is the charge, V is the speed of the charge, B will be the magnetic field. Again. Okay. Now, we look at here by using the right hand rule. Now, show the direction. Okay. Point your 4 fingers. Use your left hand. 4 fingers follow the direction of the V. Then, once you cross your finger, must point to the B, the direction of the B. So that means that we found that this will be going up. If going down, okay, going down, okay, point to B. This, we found that this will be the direction. Okay, V, direction of 4 finger is B, now going up. So we found that the direction will be in this direction. B to up, and this show that the direction of current is going in. Can you find it? By using right hand rules. Okay, how about negative? Assume this is positive first. Positive, positive Q to B. So that means that it should be in this direction. Okay. Now this V. V and F. That means that positive, it will be the B will be in this direction because this is F already. Now positive V. Okay, V to B. Okay, V to B. If this is positive charge, this will point to this side. But because of negative, negative must be opposite direction. Okay, V to B, positive charge, show that if use right hand rules, show that it will be going up. But actually, it is going down because it is negative charge. Negative charge always opposite to the direction of positive charge. As a conclusion, we can say that the force, the vector F, vector force on a charge Q moving with a velocity V in a uniform magnetic field of flux density B. Okay, flux density B, that means that is the magnetic field. It's given by F equal to Q VB, where the magnitude of the force is QVB sin delta. By the moment, the angle is 90 degrees. So sin 90 degrees is equal to 1. Later, I will show you what is the meaning of the angle not in 90 degrees. Okay, now let's look at the QVB. Okay, F equal to QVB sin delta. What happens if the proton move in this direction? When the direction of the velocity V is parallel to the direction of the magnetic field, that means that the angle is equal to 0. Okay, so just now, FB and the direction of V, FB and V, the velocity, all of them must be perpendicular to each other. All of them must be in 90 degrees. But now if B and V are parallel, nothing happens. FB, the force cannot produce anymore. Same with the electron. Okay, they must move in the direction perpendicular or 90 degrees to each other. So in this case, F equal to QVB sin delta, because the B and V, we want to find the F, right? The angle of between the V and the B is 0, A. Since 0 equal to 0, everything becomes 0. Next slide. Ladies and gentlemen, we notice that a positive charge in a uniform magnetic field which going into the screen. When a proton moves, proton will move in this direction. Okay, because now the V and the B, the direction are perpendicular to each other. How about proton? A proton move anti-clockwise direction. How about a proton? A proton will move in opposite direction. Proton and the electron. For both cases, the angle of V and the B are 90 degrees. So the angle are 90 degrees. That means that since 90 degrees equal to 1, that means Q equal to Q, F equal to QVB. Observe that the F, B, and Q, all of them are in 90 degrees. The magnetic flux density, the strength of the magnetic field. Okay, how much of the magnetic field? What is the density of the magnetic field? So B is equal to F over QV sin delta. When all of them are 90 degrees, the B and the V are 90 degrees. 90 degrees means that delta equal to 90 degrees. Okay, so the F will be maximum. So B equal to F maximum over QV. So F, where F maximum will be the maximum force produced. The Q and V, B and V will produce the F maximum when they are in 90 degrees. 91 degree considers starting reduce until 180 become none. Okay, so now from B equal to F max over QV, 1 Tesla is equal to 1 Newton over 1 Coulomb times with 1 meter per second. Okay, so the magnetic field, the density of magnetic field, we use Tesla. The unit we call that is the Tesla. So Tesla, did you hear the words Tesla before? Sure. We hear the Tesla, the name of Tesla, that is a vehicle, right? The vehicle, that is an electric vehicle. So if not wrong, this electric car belongs to Toyota. So this Tesla, the Tesla car, Tesla vehicle, now we call that Tesla vehicle, is a vehicle totally use electric without any petrol. If hybrid car, the engine can shift. Either you can use petrol, you also can use the electric. So that is an hybrid car. But now if Tesla car, the technology of Tesla is totally use electric without any petrol. Okay. Okay. Ladies and gentlemen, as a result, as a summary, we can say that the magnetic flux density B is defined by the equation B is equal to F maximum over charge over the velocity. Okay, where F max is the maximum force on a charge Q moving with a velocity v, with direction, yeah, in the magnetic field. The magnetic flux density of a magnetic field is the force acting on a unit charge moving with unit velocity at right angles 90 degrees to the magnetic field. The velocity, the direction of the velocity must be 90 degrees to the direction of the magnetic field. At this moment, this will produce a maximum force which is 90 degrees to the v, the velocity, and also 90 degrees to the magnetic field, the magnetic field density. Next, the unit of magnetic flux density is the Tesla, T-E-S-L-A. Finally, the magnetic flux density of 1 Tesla means that if a charge of 1 coulomb moves with a velocity 1 ms-1 perpendicular to the magnetic field is added on by a maximum force of 1 Newton. Okay, that means that it will be equal to 1 Newton over 1 coulomb over 1 ms-1. That is the meaning of 1 Tesla. Now we look at the slide. In a uniform magnetic field, the cross shows the uniform magnetic field. The magnetic field now is go into the screen. So the direction of the magnetic field now is into the screen. So what will happen? Once the charge, positive charge is moving, actually it will continue move in a circle if the magnetic field and the V are constant. Okay, so what happened? The centripetal force is moving in a circular motion, right? So centripetal force is equal to the magnetic force, the F. Just now we learned F equal to Q VB sin delta. In this case, all of them are perpendicular to each other, so it is maximum. F is maximum. The F actually is equal to the centripetal force of the charge. So mv squared over r is equal to qvb. So v can cancel each other. At the end, we notice that the radius is equal to the mass of the positive charge times with the velocity of the positive charge over the charge 1.6 times 10 to the power -19 times with the magnetic flux density, the strength of the magnetic field. Factor that affecting the radius. Factor affecting the radius that are M, V, Q, and B. That means the mass is directly proportional to the radius. The velocity also directly proportional to the radius. If the velocity of the charge is faster, that means the R must be bigger. And Q is inversely proportional to the Q and inversely proportional to the magnetic flux density. The stronger the magnetic field, that means that the smaller the radius. Okay, now if the proton with M, okay, move like that. Just now, the R is directly proportional to M, right? What happens if the mass increase to double? Okay, so that means that once it's become double, so it will move with greater bigger radius. Okay, so this will be the effect of the mass to the radius